it's much better. Everyone, I'm Timmy. Today we'll be talking about Africa's voice stack. About me, I lead the team at Spitch. We are a voice AI company focused on building models that enable speech to text, text to speech, as well as foundational audio models for local low resource languages like Hausa, Igbo, Yoruba. And our mission is to ensure that as we transition into the era of AI, that our languages are not left behind as we make that transition. And so our vision is that for all the technologies that are being developed, we're seeing a pattern where voice is the modality by which people are integrating and people are using AI solutions. And so that's why we're building Spitch essentially. I love engineering. I can't stop writing code. Probably should do a lot less of that these days, given the nature of the business. But I love writing code. I also like writing, just for myself and for my sanity, and I play chess occasionally. Okay, so today we'll be talking about the voice stack, and I'd like to touch on four things, structured into four parts. The first part is a crash course on audio, and let's understand how we take all these things I'm saying, how it's being processed, and how computers are able to understand them. Then we go into automatic speech recognition, which some people call speech to text. Then we talk about text to speech, and then we talk about serving and storing audio and presenting audio to users or to people. So, 1 minute. Okay. So audio is in real time, it's being streamed. And for those who did math in school, you know that there are some entities, or there are some things that are discrete and some that are continuous, right? A continuous variable, for example, would have an infinite number of possible values, while a discrete variable would have n number of values it can possibly be. As I'm speaking right now, if you were to take in everything that I'm saying, in the real world, I don't mean the digital world, in the real world, you wouldn't be able to capture everything digitally. And that's because there's an infinite number of values that I'm streaming out right now from my mouth. To make sense of this, we have to discretize it, which means that we have to, the word is sample the audio coming out. And sampling is done technically using something called a sample rate. And so we have things like 16K sample rate, 24K, 40K sampling rate. And as humans, there's a range of frequencies at which we can actually hear something, and at which it would make sense. And likewise for dogs, likewise for other devices out there. So the device themselves have their own, they've been engineered with their own sampling rates such that they are sampling from the continuous stream every second, whether it's 16,000 times or 24,000 times or 40,000 times. And so, so for us to digitally make sense of this data, this audio stream, we sample it. And the higher, as you can imagine, the higher the sampling rate, the higher the audio quality. And We also have something called channels, right? You must have seen on some audio content something like mono or stereo, right? So that tells you about like the channels in which the audio is coming in. So it could be two, it could be one. It's when it's one, it's called mono. When it's two, it's called stereo. And it just means, I don't know. So if there's some audio devices like earphones where on the left you hear one thing, on the right you hear something else. That would be stereo because it's two channels, and it's one channel which is more typical. That's mono. Then we now have this data in what is called waveform. So what we have done is we measure the amplitudes of the wave, the audio waves, and now we want to convert it to frequency, to the frequency domain. We use Fourier transform to do that conversion from the time domain to the frequency domain. Okay, so now we have the spectrogram. How do we ensure that the models out there can actually understand them? So we do this thing called tokenization. Essentially, what it's saying is we're taking the audio from the audio space to a vector space. A vector, for those who wrote linear algebra or who understand linear algebra, a vector is you could say a one-dimensional set of either floating point or mostly floating point or integer numbers. And so there are different ways by which we could tokenize. Most common ones are like wave to vec. Everybody knows wave to vec. Then we have the others from like Meta and Google, Soundstream, Encodec. These are very helpful in taking audio from the audio from like the Mel spectrogram that we talked about earlier into like the vectors that computers understand. And so once you're now speaking the language of a model, then you want to run it through that model and then use that to train it. So we've done that for audio. We do the same thing for text. We tokenize the text, and then we run it through the audio, and then we start to do a comparison between like what is generated and what is expected. For speech to text, we use and track things like word error rate. We use that to determine whether the speech to text model is on the right track or not. And then we compute a loss. The loss function computes a loss, and then that loss is used to, for those who understand, for those who understand backpropagation, that loss is used to, with gradient descent, is used to backpropagate and refine the quote unquote parameters of the model. I won't go into all the details today. That's not why we're here. But we're here to talk about audio. But this is just like the process from the input to like the model thinking and understanding of the audio to like the output. And so we refine and ensure that while training, we're using like, for speech to text, for example, you make the data dirty, you want to roughen it up, you want to ensure that this is something that that in the real world, the model would be able to understand. And the model would generalize to noise, essentially. That's what you want. And so we augment the data sets, add impurities, add noise into it. And with that, we have a much better, robust model. And as you all know, like the more data there is, the more data you throw at these models, the better they are, and then the more loss you can take off the model. Okay, So now we have like quote unquote train the model. Now you want to ensure that in the real world, like it would actually work. So you run it through evals. You for TTF, for example, we will take that to customers or potential customers and developers and say, hey, look, try this thing out. And then they score, they rank it. And then we measure things like mean opinion score. And we measure things like prosody to the degree that we can. We measure things like the speaker similarity, for example. Like there's so many things that you could measure as heuristics to help the model get closer and closer to like truth when it comes to speech to text, text to speech. And then all that is used as feedback into the next iteration of the model, essentially. So now we've trained the model. We now want to serve customers, right? In general, there's a slide missing here. It's like an inference slide. You would set up, let me touch on that a bit. So you would set up inference compute. You would set up your model, put it behind an API, have the model accept audio for speech to text, to convert speech to text, have the model accept text for text to speech. And you do that with the model parameters that the model state from when the model was performing well while you were training it. And then you put it behind an API, use fast API, use MEP for the Python developers. Typically, you use you use Python because these models are running on like PyTorch, one of the most efficient libraries out there. Some use TensorFlow. I mean, PyTorch and JAX are kind of like the go-to libraries. So in any case, you put this behind your you put your model behind your API, and you want to have an inference engine that is efficient. So you would look into tools like VLLM that is highly optimized. There are better ones out there, but you could also like customize your own, like we did internally, just for like the sake of efficiency and speed and all that, and also for cost reduction, because compute really is like the major challenge when it comes to these things besides data. And so I'll give a sample use case: text to speech. Developer makes an API call, hits our backend. They say, hey, this is some bunch of text. I want you to convert it to audio. And we ask, okay, give us like the reference audio. So we have taken some licensed reference audio that we'll use alongside the text and pass into the model. So essentially, we're telling our model, hey, here's text, here's a sample voice. We want you to generate audio in this voice. And so if you go to Spitch, for example, you see things like, you see names attached to like languages. So we run it through our model or set of models, and then these things could take time. So for the sake of like efficiency and for the sake of speed, you want to serve the audio as quickly as possible, also depending on like your use case. We chunk the text into something that is digestible by the model based on the context window that the model can accommodate. And then we take that and start to like generate vectors, which is like the output of our model essentially. And then we have a streamer internally that will take those vectors and then convert them to like raw audio. Tools you might want to look into for that are tools like FFmpeg, which is like everyone's favorite tool. And with that, we're able to reach time to first byte of like 250, maybe 300 milliseconds, which is really good. Not bad, not great, but it's good. And so we take that we take that audio, and when a user is using Spitch, for example, for AI voice agent or voice AI agent, they they get a response really quickly because they're not waiting for all the audio bytes to come back. And so the server that is being used to like stream the audio gets to or the audio to the user gets a response really quickly. And yeah, so depending on the use case, the way that the and this is back to this slide, the way that the audio is presented to users is dependent on the use case, and it differs. So permit me to do something. Let's do. Can you see my screen? Yes, you can see my screen. Okay, so these are our friends at Leadership, for example. Um, our friends at Leadership, we built something called Reader, and essentially, what Reader is, it's a tool that takes the content of an audio, for the content of a blog post, an article, and converts it into audio. So, for example, I click on this article, I can scroll down and I will see, yeah, and I'll see an audio player here. And I can just like start to play it, and we have the button. Okay, but I can start to play the audio, and it would generate the audio that is representative of this. It would generate audio that is representative of this text. So how does this work internally? We'll come back here now. We'll go to full screen. Okay. So HTTP live streaming is like a way for us to present audio in a streaming fashion to users. Essentially, what it is like a playlist. It uses two major things: a playlist, M3U8. And that playlist tells you all the segments. So each segment is a file on its own. It's a small audio file that tells you from 2 or timestamp 2 to timestamp 4, play this audio file, and then from timestamp 4 to timestamp 6, play this audio file. And that way, you're not waiting for everything to be streamed. You're essentially playing the audio as it is available. So when you go to YouTube, for example, you're not waiting for all the audio bytes to come in at once before you click play. That wouldn't make sense. You're getting the files one after the other. And in fact, when you skip, because you already have the timestamp defined in this playlist, you're in a position where you can just skip to that file and download that particular file. So that's on HLS. For real-time communication with like a turn server, so some of the developers that use Spitch would know that we have a LiveKit integration. So we have an SDK, LiveKit agent, LiveKit agent SDK, Spitch plugin, essentially. With that, we use like WebSocket connection plus WebRTC like real-time communication, by the way. Essentially, what that does is it allows it basically allows calls like this. It basically allows like experiences like this where I'm talking to you guys. You guys can hear me. Someone can speak on one end, and I can hear. So things like Google Meet, Zoom, and all that. So for communication platforms like that, the type of audio that is being returned or the format in which you return the audio would also differ. So you want to be careful about like how your, what you're returning to users, how fast the client can get it, and we'll touch on that on the next slide. So audio 3. Now we want to like store audio. We want to present audio to users. We've talked about that. Let's talk about file formats. So there are different file formats that make sense for different use cases. People are probably familiar with number 2 and number 3. That would be MP3 and WAV. So MP3, it's lossy, but it's really good. It's compressed. It's smaller, right? So for things like let's say you want to present, you're building an audio player, but the user is using a phone from 2003, right? You don't want to give them a WAV file, because that's not something that can help them, because it's going to take a long time for that device to process. You probably want to give them like an MP3, something that can easily, it's smaller, it's easy to digest. It's easy to process, quote unquote. And the only downside is it's lossy. So you're going to lose some data, which is fine, which is manageable for that use case. And then we have PCM, which is used a lot by raw audio processors. So if you use like, it's like the rawest format of audio, essentially. So if you use like almost a lot of these tools we use, audio tools we use, on the back end, like on the database, like when it's stored in like PCM, raw PCM, because it's not compressed. Everything is like intact, right? Same thing with WAV. WAV is actually kind of like a container. It's kind of like a container file format. And then we have others like FLAC, Opus. But when it comes to like training data, I don't know if you guys were in Anthony's session, Anthony of Monoscope. He talked about Parquet format. It's a beautiful format. We use it internally. So training data, for example, the thing about Parquet is it's columnar, as opposed to like your regular DB, which is like row-based. So this Parquet is column-based. And essentially, you could take like a bunch of audio, you could take a bunch of like data and like put it in column format. And like it makes it easy. It's a bit compressed. You make it easy to like read out, essentially. So now what have we done? We've described ingesting data, the process of doing that, running your data through a model, whether it's in training or in inference, and exporting that data out, returning the data to a user, and finally storing that data. That's the short version of the story that we can accommodate in this short session. So again, we've gone from collecting the data, sampling, figuring out the channel, converting it to Mel spectrogram, taking that, running it through a tokenizer, then taking that those vectors from the tokenizer, running through your model, whether it's training or an inference, and then you get vectors out, and then you convert those vectors to audio, or you convert those vectors to text, depending on the task. For audio, you need to return the audio to users. Then for that you need to consider like the use case. So we've talked all about that, and that brings me to the end of the talk. You can reach me on Timmy@Spitch.app. I try to be accessible, and you can reach me on X. I frequent there. So if there are any questions, please, I would like to, I'm happy to answer any questions. Okay, none so far.
Yep. Thank you so much, Simi, for this session.
Yeah.
Thank you for explaining a lot. Yeah, I'm just going to ask again because we have 2 more minutes. Does anyone want to drop a question real quick? Okay, means you explained very well then.
I have been told that I can be a teacher and I'll be very good at it. Yeah.
Nice. Okay. I guess we can give everybody 2 minutes back.
All right. Thanks, everyone. It was great.
Yeah.
It was great talking. Feel free to reach out to me any point in time. Cheers.
Awesome. Thanks.
Questions
Just
here.
like,
Someone just dropped 2 questions.
yeah, we have just 1 minute. See if you can speed run through them.
Okay. Okay. Sure. How many hours of audio do we use for what? That would depend on the task. But in general, we use like tens of thousands of hours of audio for a task like text to speech. Maybe even for speech to text. For speech to text, it goes into like the hundreds of hours. For what is the most challenging part about modeling? Most challenging part would be data. One of the issues with like African languages is we are low resource, so there isn't a lot of data out there. We try to find smart ways about it, but and we have like really good data partners that are very helpful, but it's still much of a challenge. How do we get data? Very good question. So we have data partners that we work with. They're able to help us out, so we don't have to worry about that. But we're exploring working with by ourselves and not running it through other companies. Slowly, we're starting to experiment with that, where we hire people to go on the platform and label data for us. It's a bit expensive, which is why we're taking it slowly. As you can imagine, what the cost is, but there's still sufficient data out there that you know we can leverage. We've also thanks to the good work of the guys at Masakane, Lanfrica. Um, there's a lot of African communities out there. But yeah, thank you. I think that's all the questions we can
Great. I'll end this now.
take. All right.